once again, here's the method of Lagrange multipliers. And the question we should be asking ourselves about is, why does this make sense? Why does this work? Why is it that if we want to find maximum values of f subject to this constraint, we look for values of x, y, z, and lambda such that the gradient of f is equal to lambda times the gradient of g. So why does this work? And so the purpose of this video is going to be examine why this works. So let's just start collecting a bunch of facts here. So the first fact that I want to write down is that the gradient of g is orthogonal to the level curve. G is equal to a constant. And so, like for example, g of x, y, z is equal to 0. That's g is equal to a constant. And this comes from, this follows from section 14.5, that discussion in there, that one of the things that we know about the gradient of a function of 2 or 3 variables is that it's orthogonal to level curves. Okay, so that's one fact. Now we need to think about the gradient of f, because remember our goal here is to argue the gradient of f is equal to lambda times the gradient of g, so we need to connect up the gradient f with the gradient of g. And to do this, we need to talk about what the book calls the orthogonal gradient theorem. Suppose that f of x, y, z is differentiable in a region whose interior contains a smooth curve. C is r of t is x of t times I hat plus y of t times j hat plus z of t times k hat. We're doing this for 3 variables. This also works if you just want to do it for 2 variables. If P naught is a point on C where f has a local max or min relative to its values on C, then the gradient of f is orthogonal to C at P naught. Before we do anything else here, I just want to make one point here, which is C, we're going to end up identify with the constraint g is equal to a constant. So the orthogonal gradient theorem does not have a g in here right now, but we will be thinking of this as the constraint curve. Okay, why is this true? Let's prove the orthogonal gradient theorem. And so it boils down to the chain rule for paths. So remember, the chain rule for paths says the derivative with respect to t of f of r of t is equal to the gradient of f evaluated at r of t dot product with r prime of t. And this is just copying down the chain rule for paths, again, from section 14.5. If P naught is a point on C where f has a local max or min relative to its values on C, if f has a local max or min as we move along, so the idea here is that, here is our C, and r of t corresponds to moving along the C here. If this point right here, if this P naught is a max or a min, what does that tell us about the derivative of f of r of t? This derivative has to be 0. Think back to Calc 1. You have a local max or min, the derivative has to be 0. We're assuming everything here is differentiable, so we don't have to worry about when the derivative is undefined. So what this says here is the gradient of f of r of t dot product r prime of t is equal to 0. This tells us that at the point P naught, the gradient of f of r of t is orthogonal to r prime of t, because the dot product of these two expressions is 0. But r prime of t, what's the meaning? Think back to chapter 13. What's the meaning of r prime of t? Like this is r prime of p naught. This is the direction vector to our curve. It's the direction vector here. So at p naught, the gradient of f is orthogonal to r prime of t, which is the direction vector for c. So if p naught is a point on c where f has a local max or min relative to its value as in c, then the gradient of f is orthogonal to c at p naught. Okay, so what do we know here? Let's go back to why does this make sense? The gradient of g is orthogonal to the level curve. G is equal to a constant. The gradient of f is also orthogonal to the curve c. But this curve c is, we're going to think of this curve c as g is equal to a constant. And so what this says here, the gradient of g is orthogonal to the level curve. The gradient f is orthogonal to the level curve. Since both the gradient of g and the gradient f are orthogonal to the same level curve, these must be scalar multiples of each other. Okay, so if gradient of f and gradient of g are scalar multiples of each other, what's the conclusion? That the gradient of f must equal some constant. We're going to use lambda here as the constant, some constant times the gradient of g. And that shows, this explains why this makes sense. We're not just pulling the method of Lagrange multipliers out of thin air. We were earlier, but now we're putting on good footing. This is why this makes sense. Let me to finish off this video, let me make a picture to illustrate this. So I'm going to do things just in the xy plane. And so I'm going to draw some, these are all level curves here of f. So right here is like, this is f is equal to 2, f is equal to 4, f is equal to 6, f is equal to 8, f is equal to 10, f is equal to 12, f is equal to 14. And let's draw this as our g is equal to c, our constraint here. G of x, y is equal to some constant. What's the smallest? Let's ask the question, what's the smallest? We want to minimize f on, let's write this up, min f on g is equal to c here. Well, right here, this is f is 14, this is f is 12, that's smaller, this is f of 10, that's smaller, this is f of 8, that's smaller, f of 6, this looks like this is the best that we can do right here. So the answer is 6, and this is a vector pointing in the direction of the gradient of f. And then we also see that the gradient of g, and we don't know which way the gradient of g of this point could be pointing this way, it could be pointing this way. But we see that they are both orthogonal here to the level curve g is equal to c, the level curve f is equal to 6. So right here, the gradients are pointing either in the same direction or the opposite direction. So this illustrates why Lagrange multipliers work.